Thank you. I'm excited about this presentation. Please feel free to interrupt me at any time. As soon as I share my slides, I will not be able to see the window with the chat window. So Alison has graciously offered to pass on any comments you may have. So again, feel free to interrupt because this is going to take, I guess, about 45 minutes, and then we're going to open it up for questions. But again, I'm completely open to questions as I present for a more interactive experience. Okay, so I'm going to share my screen now. There we go. I will try to make this full screen. Yes. Okay, can everybody see my screen? Does this work?
Yes.
Great. Okay, so the person you see here is Harold Jeffries, and this talk is inspired by his work. Okay, the outline of this talk, we'll start with the terrible, statistics hell. We'll cover the terrific, statistics heaven, and then that simple transformation that builds a bridge from hell to heaven. But before we get there, I have an amuse-bouche for you. We're going to talk about what probability means, and I'm going to provide a quick demonstration inspired by Russian roulette. And for this, I will use this, well, Nerf gun. You may know it. It's very popular in Europe, at least for children to play with. And they fire this kind of a bullet to, well, each other, I guess. And so what I will do is I will put this single bullet in this particular toy gun, and it has 4 chambers, right? And so I'm going to put it in randomly, or I'm going to have some random mechanism. Maybe I'll throw some sort of die to determine where I'm going to put this, and then I'm going to fire it once, maybe at my cat who's sleeping next to me. So we can ask, before I put it in, what is the probability that when I shoot it, I will hit my cat, right? And so there's 4 chambers. So most people would say 1 in 4, right? Okay, so this talk is essentially about the difference between frequentist methods, where people use p-values, and Bayesian methods, where you don't use p-values, but something else. And so far, both camps would agree. But now something interesting happens. I'm now going to put this ammunition into one of the chambers, right? And now I'm going to put it below my desk, and I'm going to rotate the cylinder. And I'll just keep rotating it. I have no clue, right? And now, here it is. You cannot see which chamber it's in. What is the probability that if I shoot it at my cat, the ammunition will come out, right? So as a Bayesian, you would say, well, I'm still as uncertain as I was before. So the probability, the chance is still 1 in 4. But as a frequentist, you now have a conundrum, right? Because it's either going to happen or it's not going to happen. And you really don't know, but your probability is a long-term, is a limit for when you do things in the long run. But I'm asking you about a very specific situation. I'm asking you to assign a probability to a unique event. And this is problematic. And I can make it even more problematic. What if I look, right? Now, for me, the probability is different than for you, right? For a Bayesian, that's not a problem because I have different background information. So, but for a frequentist, this poses all sorts of hurdles, right? So this is one of the key differences between frequentist reasoning and Bayesian reasoning. But this is very philosophical, and I'll make it more practical in a moment. So it's even more interesting because you could say, well, okay, now I'm going to aim it at my cat, right? And now you could say, okay, what is the probability? And I'm going to pull the trigger in a moment. Now, you know that I have looked, right? If I'm pulling the trigger, I'd be kind of a bad person if I would pull the trigger and it would actually go off, right? So you can take that into account, and it would that background knowledge would perhaps make the probability lower that if I fire the toy gun that the projectile would come out, right? So I can actually do this now. Yeah, so didn't come out, right? So just to show you, no, no, and there it actually so it was the last one. Okay, so that's just a brief explanation of the difference in the notion of probability between the two camps, the frequentist and the Bayesian camp. So in the Bayesian, from the Bayesian perspective, probability is not a property of the object. It is something that belongs to your mind. It's a degree of reasonable belief, if you will. So now to continue with the main course, the terribles, that's hell. So we have to talk about p-values and Ronald Fisher. So sometimes I tease my audience and I ask them, what is the p-value? Occasionally, I actually offer money for the correct answer. I won't do that this time. I will just give you the correct definition. So it's the probability of obtaining a test statistic, at least as extreme as the one you observed, given that the null hypothesis is true. And the thing that trips people up here is as least as extreme. So it's not the probability of obtaining the exact value, but that value or more. And if you want to remember this, you can kind of create this picture in your mind. So this is the crucial picture here. You see that the p-value is the part from where you observe to more extreme on both sides of the distribution, right? So it's a two-sided test. So the way you construct it is you say, well, suppose the null hypothesis is true. I'm going to generate data from the null hypothesis. I'm going to summarize those data with a test statistic, and this is then the distribution of that test statistic. And when the observed one is in the tails, that would, according to the frequentist reasoning, provide reason to reject the null hypothesis. Okay, so in the framework of Ronald Fisher, p-values are meant to indicate the strength of the evidence against the hypothesis. And you often encounter guidelines such as the following. If it's larger than 0.1, we have little evidence against the null. If it's between 0.05 and 0.1, we have suggestive evidence against the null. And people have come up with all sorts of poetic descriptions. It's a p-value of 0.06 would approach significance as if it's taking a walk in the direction of 0.05. But the nicest one that I've seen was that the p-value was flirting with significance. Anyway, you could describe this in many different ways, but you're in this no man's land, really. Then again, from 0.01 to 0.05, we have moderate evidence against the null hypothesis. We now feel licensed to reject it, and we may publish our result. And if it's smaller than 0.01, we have very strong evidence against the null, and again, we may publish our results. And so there's all sorts of problems with this methodology, and I would like to go over the problems very briefly and point you to the literature for a more extended treatment. So problem one, the p-value depends on unobserved data, more extreme than what was observed, right? If you keep in mind that sampling distribution, you had the observation, you had the value for the data you actually observed, but the p-value is the integral, the area under the curve larger than what you have observed. So why is that problematic? Well, here's an example. Here are two distributions under the null hypothesis, one called f of x and the other g. Now, these are the possible outcomes. X can equal 1, 2, 3, 4, 5, or 6. Now, let's assume we observe the value x equals 5. Well, the p-value for the first distribution under the null is 0.03 plus 0.01, so 0.04. Reject the null. Right? But if you do the same thing for g of x, that p-value is 0.06. Do not reject the null. So different conclusions, but the probability of the data is exactly the same. It's just that the more extreme event is less likely under f of x than under g of x. But why should that matter? Because we have observed x equals 5. Right? So logically, some people feel this is problematic. I certainly feel this is problematic. If you want, so this example is discussed in my 2007 paper, A Practical Solution to the Pervasive Problems of P-Values, and also in this other paper, which is from 2018. in a really great special issue for Psychonomic Bulletin Review. Highly recommend it. Bayesian inference for psychology. So a different problem is that the p-value measures something like surprise under the null hypothesis, but as you have perhaps noticed, I did not mention the alternative hypothesis at all, right? So it could be that we find some result, say a t-value of 2.11 and a p-value of 0.04. What can we now conclude? Do the data cast doubt upon the null? Well, we can only really say this when we have committed to H1. To illustrate, this is that sampling distribution under the null hypothesis. And the gray line here indicates our observed t-value, right? So this gives us a p-value of 0.04. And now let's say that our alternative hypothesis says the effect is relatively small. Well, what distribution does that yield? This is given by the dotted line. And as you see, the sampling distributions almost overlap completely, which means that that observed value doesn't give good evidence for or against the null hypothesis. The results are rather inconclusive. And that's because the predictions are so similar. Now, if we speculated, or if we want to test against the medium size effect, then we may have some good evidence, right? Because the observed value is much more likely to occur under the alternative than under the null. And then finally, we can have the situation where we expect a really large effect. And in that case, this observed value is actually more likely under the null than under the alternative. So you can get all sorts of outcomes, evidentially, depending on the alternative hypothesis. And without committing to the alternative hypothesis, you really can't say much. And this is explained in this paper, The Need for Bayesian Hypothesis Testing in Psychological Science. And you can find all of these papers on my website. The third problem, and this is a well-known problem, that a p-value alone cannot distinguish between absence of evidence and evidence of absence. So let's say we find a p-value of 0.35. Is this actual evidence in favor of the null? Well, it's difficult to say, right? Because the experiment could be underpowered, or the effect may really truly not be there. And intuitively, you may think that this depends on sample size. If you find a p-value of 0.35 with only 10 observations, it may not mean much. But if you find it with 1,000 observations, it may actually be some evidence in favor of the null hypothesis. So this conundrum and its Bayesian solution is discussed in this paper by Keizers, Gazola, and myself. Okay, fourth problem. Under the null hypothesis, and this is somehow for some people counterintuitive, but under the null hypothesis, as the data accumulate, the p-value drifts randomly. So it will take on every value in between 0 and 1. So if you wait long enough and you keep testing participants, eventually you will get the p-value you like. So you're certain to succeed if you are sufficiently persistent. And in that sense, p-values are sensitive to optional stopping, or what sometimes people call this sampling to a foregone conclusion. Right? So this is deeply problematic. So this is a nice example of that. Say you run an experiment, 20 participants, and you report p equals 0.045. So you're really happy about this. And then a colleague asks you a seemingly innocent question. What would you have done in the fictitious case that the data would not have been significant? So you say, well, I would have ran 20 participants more, but then I would have stopped for sure. Is the p-value still correct? Well, no, it's not. Because the answer revealed that your sampling plan was not test 20 participants and stop, but it was test 20 participants, look at the results, and if you don't like them, give it another shot. So in fact, you were planning multiple tests. And that requires a correction to keep your type 1 error rate at 5%. And this is a bit strange, right? Because it depends on what you say you were going to do had the data turned out differently than it did. So if you were smart, you would have said, no, I would have stopped for sure. right? So it starts to depend on your intention, how much evidence there is in the data. So now we can make this more silly. You answer differently. You say, well, truthfully, by the way, you would say, what would I have done? Well, if my grant gets renewed, I have the resources to I would have had the resources to test 20 additional participants. But if I don't get the grant, then I would have abandoned the project and not have tested any more subjects. Right? So now, whether or not your p-value requires correction depends on whether or not you'll get the grant. Right? If the grant does not get renewed, that p-value stays at 0.045 because your sampling plan in fact was test 20 and stop. But if your grant does get renewed, you could execute the two-stage strategy. And that means your p-value requires a correction. But that grant renewal may depend on the mood of the president of the grant panel, and who knows what their mood may depend on. So at some point, it starts to become ridiculous that the evidential impact of your data should depend on this. So p-values depend on subjective intentions for hypothetical situations that researchers may not even be aware of. Problem 5. P-values overestimate the evidence against the null. And this is a really important one. P-values just below 0.05 are not very diagnostic. And the reason for this, I'll give you the reason immediately and then I'll explain it in more detail. But the reason is p-values only look at what can you expect under the null hypothesis. Right? So it looks at one side of the coin, really. If you also look at what you can expect under the alternative, right, then you look at the balance of these two things. And so something that is really unlikely under the null can also be unlikely under the alternative. Right? And that means you still don't have a lot of evidence. So that's the intuition. But I'll run you through a cartoon that explains this, which is not based on any Bayesian principles. So it doesn't demand that you adopt some kind of Bayesian mindset to see this. So we're talking about a school project it was an empirical project about whether gargoyles prefer pigeon or chicken for dinner. So the null hypothesis says they're indifferent. The alternative hypothesis that says they have a preference. So the person in question tested 62 gargoyles and found p equals 0.05. How diagnostic is the result? So first, it's important to note that if under the null hypothesis, every p-value is equally likely to occur. Also deeply counterintuitive to most people, right? So if the null hypothesis is true, you're just as likely to find 0.5 as 0.05 as 0.005. So that's just the way they are defined. So under the alternative hypothesis, so when there is an effect, small p-values are more likely to occur than high p-values. But the exact shape of that distribution depends on the size of the effect. So if you have a large effect, then small p-values are much more likely than large p-values. And if the effect is modest, that's less pronounced. So you can have all sorts of different distributions for your p-values depending on the strength of the effect. We can discuss the diagnosticity of a p-value as the degree to which it's more likely to occur under the alternative hypothesis than under the null hypothesis. So in this case, you see the distribution of p-values under the null, you see it under the alternative, an alternative, I should say, and the diagnosticity of that p-value of 0.05 is simply the height of the ratio of the height of the curves. So that p-value of 0.05 is only 1.5 times more likely under the alternative than under the null, and that's simply not very impressive. Okay, so far so good. But obviously there's a problem with this analysis. So every true effect implies a different shape and a different diagnosticity. So how can we possibly select the right shape? Well, we can't select the right shape because we don't have a crystal ball. But what we can do is we can cherry pick the shape that gives us the highest possible diagnosticity. So out of all the possible curves we can get, we pick the one that gives us the largest distance between the largest ratio between the heights of the curves, the green curve and the blue curve. So in this case, the one that was cherry picked gives us a maximum diagnosticity of 2.5, right? So in this case, the p-value is 0.05, and you may think, oh, 1 in 20, this is good evidence. But actually, the relevant number is 2.5. The data are only, the p-value is only 2.5 times more likely under the alternative than under the null, right? That's not very surprising. So this is known as the maximum p ratio, MPR, and it was discussed by several people, Vovk and Selke, Bayari, and Berger. So it's provided automatically in the JASP statistical program that we have developed at the University of Amsterdam. And I won't talk a lot about JASP today, but it is in there. So you see, this is actually an example. You tick the box, Vovk, Selke, maximum p ratio, and that is then what you'll get over here in a table. So what does this mean? So this means that when you have p-value of 0.05, it actually doesn't mean much in terms of evidence, in terms of diagnosticity. So that's a really big problem. So people have argued for more strict cutoffs, stricter than 0.05. And yeah, based on this line of argumentation, I completely agree with that. So it would be, well, very rash and imprudent to reject a null hypothesis based on a p-value near 0.05. Okay. So, well, that's actually what this slide says as well. So let's move on, because we have quite some material to cover. I would like to move to a more pleasant topic, stats heaven. So stats heaven immediately gets us to Bayesian statistics. You see Pierre-Simon Laplace over here, really the person who first promoted and independently discovered Bayes' theorem and the use of Bayesian statistics for solving all sorts of problems. And his definition of Bayesian statistics was common sense expressed in numbers. It's also my favorite definition. So what is Bayesian inference? Well, we quantify uncertainty or degree of belief by probability. We update prior beliefs by means of the data to yield posterior beliefs. And that's really it. So we can apply this framework to model selection or hypothesis testing. You see Harold Jeffries there in the top left corner. Suppose we have two models. Could be the null hypothesis and the alternative hypothesis, could be model 1 and model 2. But we can ask, after seeing the data, which one is preferable? It's the one that has the highest posterior probability. And this is the odds form of Bayes' rule that tells you how you update your beliefs in light of the data. So we start with our prior odds all the way over to the right. That's the first ingredient. What we want to get to is our posterior odds. So after you see the data, what is the relative plausibility of the two models? And the change from the prior to the posterior odds is given by the Bayes factor, the predictive adequacy of one model versus the other. And if your model is simple, this is known as the likelihood ratio. But the Bayes factor is a generalization of that notion. So this way, the Bayes factor quantifies the evidence of one model versus the other. So if the Bayes factor is 3, the data are 3 times more likely under one model than under the other. So yeah, so this is not hell, but heaven. So when we look at the t-test, for instance, what we're interested in when we look at the Bayes factor is the probability of the data under the null versus the probability of the data under the alternative. Now, the null is very simple. It says that the effect size is 0. What is the probability of the data under the alternative hypothesis? How do we specify the alternative hypothesis? So if we were to say the alternative hypothesis specifies an effect size of, say, 0.1, then we could just calculate the likelihood ratio. We could also say it's 0.3, and again, there would be a likelihood ratio, or 0.5, and there would be a different likelihood ratio. But we don't know whether it's 0.1, 0.3, or 0.5. So what do? Well, the Bayesian solution is then to average the outcomes. So the Bayes factor is the weighted average of these likelihood ratios, and the weights are provided by the relative prior plausibility of these values, 0.1, 0.3, 0.5. So if you think a priori that 0.3 is more likely than 0.5, then this likelihood ratio will receive a larger weight compared to the other. So in order to compute a Bayes factor, we need to assign a prior distribution to these effect sizes. And yeah, that prior distribution reflects the relative plausibility of those effect sizes before we see the data. It's a prior. So Bayes factors, they condition on the observed data, right? It is predictive adequacy for the data that were actually observed. They don't depend on sampling intentions. They can differentiate between evidence of absence when your Bayes factor is large in favor of the null, and absence of evidence when your Bayes factor is near 1. And they can just be updated as the data accumulate. It's a learning process. No special measures need to be taken, and they're not as trigger happy as p-values. So just to demonstrate, I will quickly analyze the data. Well, I won't analyze the data reported earlier. It doesn't really matter, but I figured it would be more fun to look at the gargoyles. So I will switch to JASP, which I have already opened. It's an old version because I'm not on my regular computer here. And I will use the summary statistics module. Oh, wait, yes, I will use the summary statistics module. We had a paired samples t-test because each gargoyle rated the tastiness of both pigeons. And what was it? The other thing, well, I'm blanking on it. It's not important. And we had a sample size of 62 gargoyles. And if we enter a t-value of exactly 2, you see here over to your right that the p-value is exactly 0.05, right? So we can just enter the summary statistics, t-value, sample size, and we get a Bayes factor. And that is the same Bayes factor as if we had gotten the original data. So this is a very nice tool to do alternative Bayesian analysis on published data. And we see the Bayes factor in favor of the alternative hypothesis is just slightly lower than 1. So if we tick this box BF01, we see that the Bayes factor is in favor of the null hypothesis, but it's 1.119. So really, that's just 1. We can round that to 1, which means that the data are equally likely under both hypotheses, under the null and under the alternative. Right? So there's actually no evidence here at all. And that is very different from saying we reject the null hypothesis. So we also have plots, of course. We can look at the prior and posterior distribution. So what you see here is the dotted line is the prior distribution on effect size. The solid line is the posterior distribution. And you see here that that Bayes factor, again, is close to 1. Now, what we can also do, so I already explained how the Bayes factor depends on the prior distribution that you assign to the effect sizes, right? And so that's this dotted line here. And if we change the prior distribution, we're going to change the predictions from the alternative hypothesis, and hence we're going to change the Bayes factor. So what you can do to test for the robustness of your result is you can change the width of that distribution and look to see whether it still gives you qualitatively the same result. And so you can do that yourself in JASP, but there's one easy tick mark you can set that does a lot of work for you. That's the Bayes factor robustness check tick mark. So I'm just going to tick that box, and you see here the results for a wide range of different widths. So the one we used is over here, but there's other ones you can choose as well. But critically, what you can immediately see here is it does not matter how we change the width. The evidence is always anecdotal. It always falls in that bound from 3 to 1/3, right? So nowhere is this compelling. So you can do what you like with the width of this prior distribution. It will never be compelling, right? So I think that's a good demonstration of the lack of evidence that a p-value near 0.05 provides. So let me return to my presentation. Any questions so far?
Nothing has popped up in the chat yet. Feel free again to note things as they come up for you.
Good. Well, I mean, this should already shock you to your very core, right? Because this is not what you're told. You're told smaller than 0.05, reject the null, and now you see this. And it suggests that something's really amiss. Okay, so that brings us to the final part of this talk, a bridge from hell to heaven. Before we start, there's a brief commercial break. Alison already mentioned it. There's a toddler book, Bayesian Thinking for Toddlers, highly recommended. If you really want one, then you can send me an email and I might send one over. But it's also available online in several translations, actually. And this is the book that I'm doing with Dora Matzke, Bayesian Inference from the Ground Up, The Theory of Common Sense. We put in a tremendous amount of effort into this book. I think it has over 600 pages right now. And yeah, this is our own baby in a way. So I hope you like it. Okay. So this part will be about that connection between heaven and hell, and this was really just a slight extension of forgotten work by Harold Jeffreys. Now, in the next few slides, there's going to be all sorts of equations and technicalities, and because of time considerations, I will simply skip almost all of it, and instead point you to a paper that I wrote that contains all of the details. But I think for this talk, it's crucial that you understand the interpretation and the results, and not so much the statistical nitty-gritty. So this is that paper, Approximate Objective Bayes Factors from P-Values and Sample Size, the 3p square root n rule. Okay, so Harold Jeffreys developed the Bayes factor. He was the first one to propose it. And what he found, somewhat to his own surprise, is that when you quantify the evidence against the null hypothesis or in favor of the null hypothesis, you suddenly get this square root n term that pops up. And in 1936 already, he proposed an approximation of that Bayes factor that highlights that particular property. So what he did is he had a null hypothesis that says the parameter has some specific null value, and the alternative hypothesis assigns that parameter a prior distribution. And then what he did, he didn't condition on the data, but he conditioned on the maximum likelihood estimator, right? So that's kind of similar to what we did before. We conditioned on the p-value. How diagnostic is the p-value? And Jeffreys basically asks, how diagnostic is the maximum likelihood estimator? Anyway, I move on now. I'm going to skip all of this and get you to the result. Okay, and so this is basically the result. Jeffreys' approximate Bayes factor, the evidence in favor of the null, is approximately equal to the square root of the sample size times the exponent minus a half w. And w is the Wald statistic. You can see it written out here, is the Wald statistic. And this is very common in classical frequentist statistics, right? So if you have the Wald statistic, you have a p-value. So when we see that w, you're looking at a transformation of a p-value. That's one way to think about it. So bad, p-values hell. And on the other hand, we see this square root n term. And sorry, I'm gonna skip ahead a little bit. Yeah, I'm gonna skip ahead to this. So on the other hand, we have that Bayes factor. That's the heaven here. So you can see how we get from hell to heaven. It's simply adding a square root n term. Right? So this is really conceptually what's going on here. If need be, I can return to some of the slides that I skipped just now, but I don't think that would get you a lot more insight. So I was still unhappy with this because it's so general, and I was also a little unhappy with this because it didn't really bring out the relationship between the Bayes factor and the p-value. It brings out the relationship between the Bayes factor and the Wald statistic, but very few people can sort of make intuitive sense out of this. So what I did is I said, well, under the null hypothesis, that Wald statistic is chi-square distributed with 1 degree of freedom. So when we have w, we can obtain the p-value through this quantile function. And this is what that quantile function looks like. So now I try to approximate this quantile function with something very simple. And when I have that approximation, I can slot that in to the equation and hopefully get out something simple. So I tinkered for a while. And the only way I could get it to work was to do a 3-segment approximation. So this ensures that we have a relatively simple expression. So the part where the p-value is smaller than 0.01, I approximate it in this way, and that gives us, when we slot that approximation into the equation, a note, by the way, that I'm using a log here, and that equation before had an exponent, so they drop out against one another. So that gives us a very simple relationship. If your p-value is smaller than 0.10, you can get an approximate base factor by simply doing 3p square root n. Which means that if you have a p-value that is not very impressive, say 0.04 or even 0.01, and your sample size is very, very high, you actually have evidence in favor of the null. Right? So if your sample size is very, very high, you really need a very, very, very low p-value in order to have evidence against the null. So we can also do this in two ways. For the middle segment, we can have a simple approximation and a more accurate but more complex approximation. And that gives us square root p square root n. That's the simple one. And this is the bottom segment approximation. And it looks pretty bad, but actually, if you look at the scaling on the y-axis, it's not bad at all.
Good question. It's a question about BIC. And
excellent question. I have a slide on that, so we can just continue. So these are those rules, unless I skip that slide, and then I'll return to it. But I think it's still to come. So these are very, very simple rules that can get you a base factor from a p-value by including the square root n term. So we also see that if the p-value is 1, the base factor is simply square root n. So you kind of know that square root n is the maximum evidence you can get from your experiment in favor of the null. And if you have a fixed sample size, if your p-value is smaller than 0.10, the base factor is proportional to the p-value. So that means that if you go, for instance, from a two-sided to a one-sided test, and your p-value is below 0.10, that actually does mean that you double the base factor. And there's also this intuition that I mentioned before. It was actually due to Bergson, that the same p-value will actually be evidence in favor of the null when your sample size is large, right? Because there's this square root n term in that evidence. Now, the equation also says something about optional stopping. So as sample size increases, that p-value is randomly moves about, but not if you add the square root n term, because the square root n term drives you in the direction of the null as you get more and more observations. So that's also really neat. So you can get a really quick evaluation of how strong the Bayesian evidence is given a published frequentist claim. So I hope let me go back, because I think maybe I say something about here I have it. So this approximate base factor is very similar to the BIC because that also has that square root n term. So Jeffrey's approximate base factor was discussed by Cousins in a great paper, but has otherwise been forgotten. And so what Jeffrey's did kind of anticipates, and there's some advantages and disadvantages to both, but I don't have time to discuss that now. So what I would like to do is I would like to show you how well the approximation works, right? And the approximation is meant to apply to our default base factor settings. You can tinker with the priors and you can adjust the formulation, but here I'm just going to talk about the default priors. So here we go. This is a one sample t-test. So on the x-axis, you see an accumulation of participants. The black line is the p-value, the classical p-value, right? So you see that it drifts randomly, and at some point it actually hits the 0.05 level over here and over here, and I think all the way at the beginning as well, but let's ignore that. That's a very low sample size. And here on top, you have the different colors, and they are the posterior probabilities for the null hypothesis if we assume that both the alternative and the null are equally likely a priori. Then we can also get a posterior probability for the null, and then we can put it on the same scale. That's why I did that. And the different colors represent the different posterior probabilities that you get from the real base factor and from the different approximations. And you can see that they almost completely overlap. If we can do another application, a test of two proportions. I used a particular default Bayesian test. I don't really want to get into it, but you see the same thing. P-value meanders randomly and starts telling you here and over here, reject the null. But the approximate test, the approximate base factor, gives a different result. And also the approximation is very close to the real thing. Actually, when I did this, I was very surprised at how well this worked. And you may say, well, but look at your observations. This is very large, right? Of course, approximations will work if you have this many. But we can zoom in to the first part and look at the first 250. And you see that from a very early stage, the approximation is very close to the real thing and very different from the p-value. And this is for a correlation test. Same thing, p-value does random things, and the approximation is extremely good. And we zoom in again on the first few observations, and we see that it's extremely good even for very few observations.
A question about the tuning parameter here.
The tuning parameter as in the parameter for the prior distribution, I assume.
That's my assumption too. Feel free to clarify in the chat.
Yeah, but that's really important because I'm looking here at the default tests. And for instance, the default test for the correlation, which is what we're assuming here, is that there's a uniform prior on the correlation. So every value from -1 to 1 is equally likely, right? So sometimes, of course, you want to do something else. You have prior knowledge and you want to change this. And the nice thing about Jeffrey's approximate base factor, when you compare it to, say, BIC, is that you can actually incorporate that into your equation. Of course, it won't be 3p square root n anymore. It will be something slightly more complex, but not very much more complex. And to extend that 3p square root n formulation to easily handle informative prior distributions would definitely be interesting to do. Okay, so to conclude, p-values are tormented by a series of deep statistical problems. And not only this, as we've seen with our initial example, the whole concept of probability is very different between the classical paradigm and the Bayesian paradigm. So you may think that these are two completely different worlds. They are as different as heaven and hell. Base factors do not have any of those p-value problems. But miraculously, this very simple transformation of the p-value provides an accurate approximation of the base factor. And so, yeah, it's really came as a complete surprise to me, actually, that it did so well and that we can bridge these two incompatible statistical concepts this way. People have done similar work in the past, but what they've mostly done is say, construct an upper bound, where you say, if I have a p-value, the base factor can be no stronger than this. But that's, of course, providing an upper bound is very different from providing an actual approximation. So yeah, that's what I want to leave you with. And I hope you feel inspired to use this methodology and certainly the Bayesian methodology in your own work. And of course, apply JASP in order to do it. Thank you very much.
Thank you so much. So we are open for questions. And while people are thinking, I will pose the first one, which is that, we have the delight at Spark to hear a lot of talks where people are really challenging some kind of classics of statistical teaching. And every time I have a flashback to the statistics courses I have taught and the things that I have said and went, oops. How does this look in terms of how you and colleagues within your department approach teaching elementary statistics to students?
Yeah, that's a great question. So for a long time, whenever I was asked to teach statistics to our first year undergraduates, I would say, that's fine, but I'll teach them Bayesian statistics. And that got me off the hook immediately. But no, what we've done is we are now teaching our first year undergrads Bayesian statistics in addition to classical statistics. So so they get a lot of descriptive statistics, of course, and then they get inference, and it's mostly classical, but I think they get 4 classes of pure Bayesian statistics. And then in the second year, they get some more. Actually, there's another course in the first year that I co-teach where we provide more Bayesian statistics as well. And then in the second year, this continues. And the event that I like the most is I have a colleague, Danny Bosboom, and in that first year course, at the end, we have a debate. So he's the frequentist, I'm the Bayesian, and then we debate for 45 minutes. We first have a presentation, then we debate a little bit, and then the students join in. And it's always really a lot of fun. And then he doesn't know yet that I will use this in my debate with him, and I'm probably going to fire the thing at him. But yeah, it's a lot of fun. So no, students totally dig it, and also the idea that statistics isn't a set in stone, but it's something you can think about, you can disagree about. It's the discipline is very much alive, and I think that is something that students like to see.
Absolutely. We've got a comment in the chat about great interest in Bayesian statistics. And I would say Bayesian statistics is not broadly taught at McMaster University, and I am a Bayesian, and it's been a surprise to see, how resistant.
Yeah, well,
what the resistance to it is.
But so I wrote a large grant proposal, fingers crossed, and my usual pitch is Bayes is really great, but people never use it or don't use it as much as they should. But when I started to write this proposal, I thought like maybe I should actually test this and do some empirical research before I make that claim. So I looked at Psychonomic Bulletin and Review last year, 2020, 2023. And I simply counted the proportion of articles in Psychonomic Bulletin and Review that reported at least one Bayesian analysis. Right? So guess the proportion of articles in PBNR that report at least one Bayesian analysis. So anybody? So my personal guess was 5%.
1 in 20?
Yeah, see, 5%. Yeah. No, it's percent.
Oh.
So I think that I was very excited about that. So now we started a much larger project to look at that in more detail. But I think we are in a Bayesian revolution without knowing it. So there's a steep increase in the reporting of Bayesian analyses. And I think as that increases, the pressure on curricula will increase as well to accommodate this in their teaching.
There are questions, comments, thoughts on this? Anyone have your eyes rolled up in your head going, oh my goodness, what do I do with this?
Can we use HQs instead of PIC here?
Sorry, what did you want to use instead of PIC?
This is called a Hanan-Quine's information criteria.
Oh, yeah. So it's funny you have these information criteria. I think I'm not 100% sure, but I believe every letter of the alphabet you can put IC after, and it will be a valid criterion, right? You have CIC, DIC, EIC, FIC, GIC.
Yes.
So they all have their pros and cons. Why I like the dynamic of the BIC is it does two things that I find are really important. So the one thing is, well, actually BIC, so I'll focus on one thing. If the null hypothesis, if the simple model, in this case, the null hypothesis, is true, as you accumulate more observations, you will actually discover that that's the case. So it's consistent, the method is consistent under the null hypothesis, and virtually everything else is not. Actually, minimum description length, there's also a minimum description length principle you can apply to model selection. That's also consistent. And that has the same dynamic. But everything else is not. For instance, cross-validation is not. On a specific type, most kinds of cross-validation are not. And that's if you do cross-validation and you do, for instance, split half, right? So you feed the null hypothesis the data and you feed the alternative hypothesis half of the data, and then you look at predictive performance for the half that you left out. It looks like a fair procedure, but it's not. And why isn't it? Because the null hypothesis doesn't benefit from the data because it says there's no effect. And then it gets half of the data and all it says is there's no effect. But the alternative hypothesis does benefit from the data. And if the null is true and you feed the alternative hypothesis half of the data, then the alternative hypothesis will start saying there is no effect. And then you have two hypotheses that say there's no effect. And then the second half of the data is not diagnostic. So it's very difficult, therefore, to provide evidence for the null. So you kind of need a BIC style dynamic in order to be able to have increasing support for a true null, which I think is, for me, it's kind of a minimum requirement, honestly. But opinions differ.
Okay, so
some people really hate the Bayes factor, so and BIC as well.
Molly has a hypothesis in the chat that the Bayesian revolution might be due to the crisis of replicability in psychology. That, you know, we all know that p-values are inherently problematic. We just don't always know how to move away from it.
Yeah, that's that's interesting. So I do think that a Bayesian methodology would help a little bit, right? It would prevent problems with optional stopping. Arguably, there's a debate on this as well. And it's not as trigger happy. So that would help as well. But I do think that the larger issue with the crisis of replicability is that people who do the research are highly invested in the outcome and will do whatever it takes to get their paper published. And there's no statistical methodology that's robust against the deep desire of the researcher to see their hypotheses confirmed, right? And certainly once you start to cherry pick and leave out data you don't like, right? No statistical method can deal with that. So I think there's deeper problems. I do think Bayesian inference is a step in the right direction, and it's kind of a package deal, right? Open data, pre-registration, Bayesian analyses, kind of shows the world that it sends a lot of good signals. But yeah, I think there's deeper issues than statistics at play here, unfortunately.
On that note, thank you so much, and thank you for joining us. We've been Oh, sorry, one more quickly. Why can't we use Jeffrey's prior so easily?
Oh, well, now we have to be very careful. So there's two kinds of priors. Jeffrey's proposed two kinds of priors. One for estimation. This is when you know that the alternative hypothesis is true and you want to estimate the size of the effect. And the other one is for testing. And they're not the same prior distribution. And it's confusing, and it's not what a subjective Bayesian would do, who just has a degree of belief, and this is my prior, and that's just it. But yeah, if it would be a mistake to use his priors for estimation for testing. And the idea is this: the priors that he uses for estimation are extremely wide. And you cannot really use that for testing. And the reason is this: you may think, oh, but an extremely wide prior distribution is a perfect reflection of my ignorance. So why can't I use that? Well, the thing is this: it's not ignorance. If you have a wide distribution, it actually says, I'm completely confident that the effect is huge, right? That's what that says. And so if the effect is not huge, you will get severely punished. So that's the really interesting aspect of that. So you have to be really careful. There's a paper I wrote on the Jeffreys-Lindley paradox that I highly recommend that explains this in painful detail.
All right. Thank you, everyone. And thank you so much, EJ Wagenmakers.
Yeah, thanks. This was a lot of fun. Thanks, everybody, for attending.